All right, so there are three types of double displacement reactions we're going to talk about. The first is a precipitation reaction, which is basically just the creation of a precipitate as a product, and we'll talk about what that is in a few moments, but again, that is some sort of solid product, okay? The second is an acid-base reaction, and an acid-base reaction, which we're going to talk about right below here in the slide, involves some sort of transfer of what we call a proton. Now, this term proton is a little bit different here than what you're used to. So we in chemistry in the acid-base chapter refer to a proton as an H+, okay? And that H+ is because we call that a proton. Now here is a basic Bohr diagram of just hydrogen here, okay? So I drew hydrogen, and we know plain atom hydrogen has one proton and one electron, no neutrons. Now when that becomes an ion and has a positive charge, we see that it loses an electron. So therefore, all that we truly have with an H+ is one proton, which is why when we say proton, we actually mean an H+. So those are interchangeable terms we're going to use throughout this year. So I just wanted to clarify that. And then the last one is oxidation reduction. And oxidation reduction we're going to get into a little bit later on in the year, but basically that is the transfer of electrons between reactants. So as we said, let's look at acid-base. So there is a couple different terms or definitions for acid-base. The first is Arrhenius acid and Arrhenius base, and this is a little bit of an older term for it. But an Arrhenius acid is one that when it dissolves or when it breaks apart, it creates these H+ in the solution. Okay, and it has to, of course, dissolve in water. So it's usually some sort of strong acid or so breaking apart, and we see an H, and then we see its anion. Now, Arrhenius base is the opposite here. We have a substance that when it breaks apart, it actually creates hydroxide ions. So we're going to need to know that term hydroxide for OH-. So for example, NaOH breaks apart into its cation and its anion portion of OH. Now, the more common term we're going to be seeing a lot more and utilize is the Bronsted-Lowry acid and base definition. And a Bronsted-Lowry acid is one that donates a proton, and remember we're going to say proton, but we really also mean an H+, to another species. And the other thing has to accept it, and the thing that accepts it is called a Bronsted-Lowry base. So basically, here we have an acid, we have a base, and one of the H's here is going to transfer from the acid to the base because a base is a proton acceptor. Okay, where an acid is a proton donor is how we say that. So then ignore these terms, acid base, conjugate base. We may get to that, or you may learn that in Chem 2. But the acid loses the H, and it is now left with just one O and just one H, and then the base has accepted it. Okay, so it's basically the transfer of that proton or that H+. Now, to understand the Arrhenius acids and bases, you have to memorize the strong acid list. So I have highlighted here to the right, and so we have 7 strong acids that you need to know, and you will need to recognize these as strong acids or strong bases because you have to recognize that they are Arrhenius acids. Now, all of these molecules do break apart, so we're going to see this term dissociates quite often. That just means that 100% breaks apart into its ion. And you can see that here. So this is an example of a dissociation reaction. We have the H+ and the Cl- breaking apart. And so all of these strong acids break apart. They have their H portion cation, and then they have their whatever the other portion is, anion. So when you see it's a strong acid, we know that it breaks apart completely 100%. Now, weak acid is basically anything that has an H in front of it and is told you that's an acid, but isn't one of these strong acids. So an example here is this vinegar solution. Now, we do use the term dissociates, but when you see this double-headed arrow here in this example, it means it goes back and forth. So we do not see with weak acids 100% dissociation. To be honest, you don't have to memorize this, but it's only about 1 to 5% of breaking apart. So if we had a solution of this, we were working with it in lab, about, 95% of it would be this whole complete HC2H3O2, where about only 1 to 5% would break apart into its H+ and its anion of C2H3O2-. Okay? So big difference between strong and weak acid you have to know. Strong acids break apart completely into H+ and whatever their anion is. Weak acids, not very much breaks apart. Okay? And you have to memorize the strong acids. Now here's a picture representation of what I was just talking about. So here we have here on the left, figure A, a solution of HCl. Again, when you see HCl, I want you to know that that is a strong acid. And we can see here that when it breaks apart, we have a ton of the Cl molecules here. And we also have a lot of water molecules left. Now, another thing I want you to be comfortable with using is when you see H3O+, that's actually another way of saying H+. That just means you have an extra H on top of water. So although we know HCl would break apart into H+ and Cl-, a lot of times you're going to see it as H3O+ as well. So these are interchangeable, okay? And so let's compare this to the weak acid here. And again, anything that has an H in front of it that is not a strong acid that you memorize is considered a weak acid. And so this weak acid, when it breaks apart, as I told you, only about less than 5% breaks apart. So when you look at the pictures here in the figure B, you can see that most of these are still HF molecules. They're not broken apart. Now there are a couple that are broken apart here. So there's an F- here. We see one of those here, but most of these are still whole molecules, and we have an H+. All right. So big difference: break apart completely. Strong acids don't break apart very much. Weak acids. And the same is true for Arrhenius bases. Again, you do have to memorize these bases, and so they're in mostly group 1 and 2 on the periodic table. That may help you memorize them. But again, these dissociate or break apart 100% of the time, 100%. So we use a single-headed arrow for this, and that means all of the NaOH breaks apart into the cation and this OH or hydroxide ion as well. Okay, so Arrhenius means it is donating that OH-. Now, just the same, when we have any sort of weak component, we have this double-headed arrow, and remember that means that this reaction is just going back and forth. It is not continuous in one way. We call it reversible. So we see that, yes, it did break up, but remember, only maybe less than 5% of this solution is breaking apart. Okay, so difference between strong and weak bases is the same as strong and weak acids. So let's go ahead and classify these. So go ahead and pause and try to see if you've memorized your strong acids and your strong bases. And I'm going to go ahead and do them as well. Oh, excuse me. Looking ahead here. This is actually a weak base. Please excuse me about that. Okay, so again, if it is on your list of weak base or strong bases or strong acids, it is easy to identify. So again, once you have these memorized, you will be able to clearly recognize these as strong acid, strong base. Now, how do you know it's weak acid or weak base? Well, when it's an acid, it has some sort of H in front of it, okay? And it's not a strong acid, therefore it's a weak acid. And then the opposite is true as well. You don't know much about AlOH3, but you know it has an OH, and therefore it's not a strong base, so therefore it's a weak base. Okay? So memorizing the list is what's going to help you here. Now, whenever acids and bases are put together, such as baking soda and vinegar, they neutralize each other. And neutralizing just means they're kind of counteracting the opposite properties that they have. And so when we have a neutralization reaction, we also call that an acid-base reaction. And these are always going to be double displacement. Now, the products of a strong acid and a strong base, which you would have memorized, is water, in the way that we literally write H2O, and that is a liquid. Okay, this is an L. And then a salt, and I want to remind you, a salt is just another name for a compound. So it is not NaCl, it is just some sort of salt. And you can see this oftentimes because it is usually an exothermic reaction. Heat is being given off, it is exiting the system. Now, you've probably done this in Intro to Chem, but you are going to be using at some point when you do a titration, we use a color change to indicate that we have gone from an acid to a base, okay? And so an acid to a base color change, we use an acid-base indicator. The most common acid-base indicator that we use is phenolphthalein, and that changes from clear to pink when it's a base. And so instead of using a pH meter, we can just use color changes to help us figure out if something is a strong acid, a strong base, or a weak one of those. Now, there's a couple terms here. We have monoprotic, so let's just break that apart here. Mono always meaning one, and protic meaning some sort of proton, and we now understand a proton is also called an H+. So monoprotic means literally one H in the formula, where polyprotic, poly meaning 2+, and protic being protons again, means that there are multiple H's. Okay, so the only strong acid that is polyprotic is H2SO4. We also have a strong or a weak acid, H3PO4, that is also polyprotic, just so you know that there are others. So this was a strong acid, and since this other one is not a strong acid, we automatically know it's a weak acid. So as long as you memorize those two lists, you should be good. All right, so let's go ahead and just do some double displacement predicting products. And so we call these neutralization reactions, but honestly, you don't have to recognize them because you just do double displacement. So just a quick reminder of double displacement. You are changing the partners, so a cation is going to be switched with a different anion. I like to do outer and inner, so BaNO3, barium has a +2 charge, and then HOH. Now, some of you may like to write that H2O, but if you will trust me in this, it's nicer to write it as HOH because you can clearly see the acid and basis components on there, and in the future that will be helpful, but of course H2O works as fine as well. I'm going to do this one, NH4, joining with sulfate, and HOH. So again, remember, water, which we're seeing here, and some sort of salt or ionic compound. And again, an ionic compound is a cation and an anion, or a metal and a non-metal. Just those two definitions both work. And this last one is K3PO4 plus H2O, okay, or HOH. Just wanted to show you both options. Okay, either one of those is fine. All right, so this is a little bit of practice of net ionic equations. We have learned net ionic equations. If you need a little bit of a refresher, please go back to the previous video. So go ahead and pause this and try to do the net ionic equation. You're going to want to write your molecular, then your complete ionic, and then your net ionic, and using your solubility chart to figure out the phases. Now, with this, I do want to remind you, H2O is a liquid, or HOH is a liquid, and you do not separate liquids. You only separate aqueous solutions when you're doing a net ionic. Okay, so we're going to go ahead and look at the answers on the next slide. So again, we do not separate this. We separate anything aqueous, and you can see it being separated, and the spectator ions existing here. Okay. So our spectator ions were the 2K pluses, and then you have what's left over here. All right, so for a reaction to occur, a double displacement reaction, there's a couple reasons why. You either are creating some sort of solid, which we call a precipitate, as a product. You are forming some sort of water, which we know to be an acid-base reaction. You're forming a gas, which we'll see here in a few moments, or you're transferring electrons, and we call that oxidation reduction. So if you're creating some sort of gas, you've probably seen this in lab, but anytime you're seeing any bubbles as a product, usually that means gas is being released. Oftentimes it's CO2, it could be SO2, sometimes SO3. So anytime a gas is created, that's another reason you could have a double displacement reaction occurring. So as I said here, some very common ones, you don't have to memorize these, but if you get a product of H2CO3, you know that could actually further break apart into H2O and CO2, and that CO2 would be the gas that is being released. Same thing here, that SO2 is the gas being released. Now another option is also H2S, which you would have that, that rotten egg smell. Okay, and evidence of something like this happening is bubbles. So we can go ahead and do another example of some double displacement reactions. I'm going to go ahead and fly through these. Now, I'm okay with you leaving this as H2CO3. You may have some professors in the future that prefer you to write that as H2O plus CO2. So it'd be KBr plus that. I am not going to require that, but again, I just want to show you both options, either this option or this option. Okay? Go ahead and erase that. Okay, let's go ahead and do this other one here. So MgCO3 Cl2. And same thing here, H, I'm just going to do H2CO3. And that could break apart into the same HOH plus SO2. So gas-forming reactions are very easy to see because one of your products has a G next to it, and I said to you, these are 3 very common gases that are produced. And I said you don't have to know how to predict the products. I'm not expecting you to know how to simplify H2CO3. I still expect you to be able to predict these 2 products, but I don't expect you to break it apart into the gases that it would make up. So we have another example of molecular ionic and net ionic equations, and you can go ahead and complete this, pause the video, and then you can check your answers on the next slide here. Okay, and I want to remind you, you do not ever separate solids, and you do not separate liquids either. Okay, you only separate aqueous solutions.